I'm ready whenever you guys are.
Cool. All right, time for our next talk. This is Evan Jensen with the Backdoor Foundry.
Hey, what's going on, everybody? I'm actually not certain that the projector is working. Sorry, false start. All right, here we go. So, hey, what's going on, everybody? Title of my talk is the Backdoor Foundry, toolchain for building application-specific implants. So, what does that mean? Why does anybody care? Let's talk about the life of a binary. This is a pretty familiar diagram. I think everyone's probably seen it more times than they care to recount. It describes the process by which you go from source code to having an application running in memory. And there is a specific part of this chain that I care about, and it's what happens right at that lower transform labeled link. And what I was able to do is introduce a loop here whereby you can take a fully compiled binary and link in additional shared object files. And why is that significant? I think it's significant because it enables anyone, essentially, who knows how to drive a compiler to install arbitrary software into arbitrary applications. And that's really nice, and it's an improvement, I think, on the state of the art. So why would anyone want to do this? You might want to modify, upgrade, improve, repurpose existing software. I think it's certainly nice to be able to write modifications in high-level languages as opposed to in assembly, which anybody can do, but it's time-consuming. And if you're writing in assembly as opposed to high-level languages, you can't really capture any of the gains made in software engineering in the last 30 years or whatever, or longer now, right? You may want to remove functionality from applications you encounter. You may want to alter functionality in applications you encounter. Being able to do that all in C, really super familiar. And then I want to just draw everyone's attention to the last bullet point here. This is what everyone says they work on when I ask, so I don't know. It's good for this one too. Stuff. So this is a little bit about me. I'm not going to spend a lot of time here. I know just we're running a little bit behind schedule. A sampling of the organizations I've been a part of, my educational history. The icon in the lower right, that's my favorite organization. Let me tell you about that one. That's the one that I started with a couple of former coworkers in 2017. We focus mostly on training and research for the defense industry in the United States. The Twitter handle for the company, more than welcome to follow it. Appreciate it if you would. So a little more on the background, other technologies in the space. Why take this approach as opposed to any other approach? So this kind of thing that we're doing, this belongs to a family of technologies known as static binary instrumentation. There's a related family of technologies, dynamic binary instrumentation, examples of that. I guess a debugger, technically, depending on how you use it, Valgrind, Dynamo Rio, pin tools, etc. It's not really what gets me excited. I care a lot about static analysis and things that happen, things that you can do, things that you can look at just by thinking really hard, not necessarily observing what actually happens. There's a wide range of SPI technology. It goes by all kinds of different names. There are a couple of them there, more detailed list. I guess if you had to classify what the thing that I'm working on to be this point right in the middle, which is like a software injector, software infector, right? I'm less interested in binders and joiners. These are pieces of software that can take two disparate applications together, run them both. Typically they'll present as one or the other, but they'll run concurrently, typically as separate processes, and there are all kinds of reasons that you may or may not want to do that. And then at the very top you have things like pactors and cryptors, and totally distinct from joiners. So I mentioned some of them, but a couple more of the goals for a project like this. You want to extend, arbitrary executables. Why arbitrary executables? Why not recompile from source when you encounter anything that you want to modify? Well, you may not know for certain when you encounter a given piece of software if it's been unmodified before you got there. So, if you are on a system and they have like a modified dynamic linker, for example, and you recompile any given dynamic linker and replace it, you don't have strong guarantees that the software that you write will have the same functionality set that was there in the system originally. So it would be nice to maintain the sort of binary functionality of that software. You want to leave it essentially intact and only add things around it, or perhaps alter the metadata that describes it. You want to be able to use high-level languages to describe the types of manipulations that you're going to perform. And it would be nice when you're writing that high-level language if there were no requirements that the people that were going to write those had any kind of like specialty skills. It would be great if you could just enable them to be written by sort of ordinary application developers. And it would also be great if there were no constraints on what kind of languages you support. So any compiler, because essentially what this piece of software is a linker, it'd be great if you could just support any compiler that would emit a standard ELF relocatable object, or maybe in the future any kind of relocatable object for any kind of file format. So I indicated that this is like belongs to the family of SBI. There are no shortage of sort of previous SBI projects. Here they are on a spectrum from heavy syntax modification to light syntax modification. Our stuff falls right in the middle, very similar to the Backdoor factory and others in there as a file injector. There are, this idea is not new. There have been a couple of publications. One of them is really great. I think it's my favorite. It's from Frack in 2003. Definitely read that. It contains a lot of in-depth information about how to do this stuff. There is one technique that they missed, and we'll talk about it a little bit later. And then while I was doing research on related techniques, I encountered this, which is an excerpt from the manual for the LD utility on IBM's AIX operating system, and it's really interesting. This is actually a feature of this linker. Reading between the lines a little bit, and I don't know if anyone here works for IBM. If you do, I'd love to talk to you. But it seems like, given an application, I think reading between the lines, it seems like you have to have built it, but given an application and a shared object, or a relocatable object, you can just replace an existing relocatable object in a program with whatever. All right, so let's talk about how one might go about doing this. So you may be familiar with sort of how a standard ELF file infector works, but if you're not, this is a primer. You have some code, and you have a target ELF application that you want to modify. So you need to understand how your sort of target application understands the code which is inside of it, how it describes it, and how to modify those descriptors so that you can run your code. It's also important that you get your code into memory. So the thing which describes how the data on disk ends up in memory is the records in the program header table. It contains these records known as load records. But the program header table, where it exists in the ELF by default, is typically packed in next to other data elements, so you can't necessarily extend it without corrupting something. You can always move it to the end of the file, where conceptually you have infinite space and you don't have to worry about that problem. Then you can extend it and insert as many records as you want there. Now, just inserting it is not enough, because all of the metadata in the ELF file still references the old program header table, but there's really only one field there, and you can rewrite it without much trouble. And at this point, if you've done these modifications, then you can load anything from disk at any point into memory at any point, but still not necessarily great enough to be able to run arbitrary code. You have to be able to detour the some pointer which would invoke code, ideally early on, or typically done early on. At this point, you can insert your code after having inserted a program, a load record in the program header table, detour a pointer, point it to your stuff. Now, of course, your code, either needs to spawn a thread or just branch back to the original code at some point if you want to maintain the functionality of the original application. But if you have software that does this, then you have pretty strong guarantees that the original application will work as intended, because you haven't modified any of the code or any of the data describing it, or any of the records describing how it loads. So keep that in mind as we talk about this next little bit. So, a lot of ELF file infectors that you find on the internet, and all of the ones in my slides, they're designed to insert shellcode, which is, has drawbacks. It's easily signaturable. It's can be very challenging to write. It has, behavior which is sort of characteristic of shellcode, and I don't really want to have to operate within those constraints in terms of development or deployment. So what we do is we create an ELF that we use to extend a target application. And the extension ELF is we create it by applying a process called partial linking, which enables you to take a bunch of disparate.o objects and link them all together. Then, similar processes I described earlier, we can extend the ELF program header. And the difference between a file infector and what we're doing is that we're going to apply linker techniques to make sure that we can insert whatever we want, namely compiler output. Compiler output has all kinds of metadata describing how to link it against other things, and we can leverage that through the process known as static relocation to insert arbitrary code. Once you apply static relocations, now you have a chunk of code which you can insert relatively painlessly at a target address, and you can expect that it won't crash. Not all static relocations, however, not all relocations can be applied statically, however. If you consider how dynamic ELF executables work, there's like a table of function pointers known as the global offset table. So those are relocations, but they can't be applied statically. They can only be applied at runtime. So if you have relocations which can't be resolved statically, you save them, they become dynamic relocations, and there's a special place in the ELF metadata for them to go. After you fix up all of the ELF metadata, then you just detour a function pointer or something else to acquire control flow early on. So I'll show you a simple example of what that might look like. So here is a screenshot of a record in the init array. The init array is an array of function pointers, which is called by a function typically emitted by a compiler called the init function. You can insert as many pointers as you want here, and they'll get called in order. So you can leave the entry point, for example, in place, and that's useful because if the application crashes at any point, then the stack trace will look sane, right? There won't be something suspicious before main. You also get to run before main, so if you want to modify anything that happens early on in main, you're free to do that. So the function pointer I've inserted here points to some code that I've inserted. You can take a look at that, and that here on the left-hand side is a very simple program, which I applied the algorithm that I talked about to. It just calls puts with the string hello world. And if you look in the disassembly there are a couple of indicators that indicate that the relocations have taken place. For one, pushing the offset to the string hello world. When your compiler emits that as a relocatable object, it looks a little bit like this, where you can see here on line 16, for example, that there's a load effective address into EAX from EVX plus 0, and then again 2 lines later. Those plus zeros, they don't exist in runtime. This is a snippet from the start function. So it's redundant. It doesn't make any sense. Elsewhere, this is the disassembly text, of course. Elsewhere in the ELF, there's a record describing how these things get fixed up. And then, oh, geez. Oh, that's bad friends, What are you going to do? So, when these get fixed up, you've probably all seen a function that looks like this. It has sort of sane data here. You can tell that these are pointing at different data elements in preparation for a call to libc start main. So, you take your compiler output, you apply your apply relocations to it. You can now, insert it because it will, behave like real compiler output. This is some example of different types of relocations which exist for x86 programs. Here are 3 ones which are really nice. The first one is a relative relocation. So you might want to emit these, where you need to maintain some kind of relative distance from another data element. The next one down, R386PC32, is the absolute relocation. So if you have a, certain types of move instructions, for example, take an immediate operand, which is a pointer, and it's very challenging for a compiler to emit like a constant pointer in the presence of ASLR because it will always be wrong. So the compiler knows that this will always be wrong. It emits a absolute relocation record, and that will work at runtime. And then this one's really interesting, R386copy. This enables you, if you can emit the appropriate relocation records, you can control a mem copy, the source and the destination, the size, which is, this is on an exploitation context. It would be very useful otherwise. But what it does enable you to do is kind of prepare what you have on disk in any way you want, and even in ways which don't make sense in the context of runtime. And then, you can emit one of these which triggers dynamically, which will carve up your stuff at runtime, make it look how it's supposed to look. So let me tell you a little bit about how we can drive the process of the creation of these dynamic relocations. So you want to emit dynamic relocations, for example, in the case where you're trying to manipulate a binary that does not use a certain function in libc. So for example, if you want to, as part of your manipulation, call a function like printf, but the target binary doesn't call printf, then there won't be a PLT entry, there won't be a GOT entry. But because you control, at the time that you're rewriting a binary, you control the dynamic relocation entries, you can always emit them. And some of those some of those functions that you may want to call, they might exist in libraries that the target application doesn't support. And so it would be nice if you had an application development environment which could capture information like that. And C++ namespaces do that quite nice. And then these are names which are chosen to be interpreted by the tool. So the load namespace indicates that the next level of namespaces represent shared objects which need to be loaded. And here's what that can look like. There's a table in ELF called the dynamic table. You can see at the top that there are just certain records which admit that you need to load these libraries. And so you can control that with a data structure like this. Also, C++ I really like a lot, and it has the modern C++s. They have a lot of really neat features. So the decl type keyword enables me to just sort of steal the type declarations of functions I'm interested in. So in libc.so decl type malloc pointer is a function pointer with the same signature as malloc, and then I can emit a variable called malloc, emit subsequently a dynamic relocation for this, which will write the real pointer of malloc here at runtime. So I never actually assign this anything. It just looks like 0 until runtime where it gets the pointer for malloc. Then you can call it as if it were malloc. And you can include all the .h files and everything. Everything makes sense. It's just like writing normal C++, except you have one extra link in your build chain. I'm going to release this proof of concept that I have. I just have to squash one or two bugs that remain, so that it's good and fully usable. I'd also like to clean up the code a little bit. I don't have the kind of best coding style at times, and so I'd like to make this something that I can be proud of. I'm doing a little bit of travel after REcon, so expect this release in about 2 weeks. So just super quick summary. Developed a tool that enables you to compile sort of arbitrary programs, but predominantly in C++, and then insert the compiler output of that into applications of your choosing. A couple of different methods. I showed you one, which was to steal or to insert an arbitrary pointer into a init. There are a couple others. Future work would like to extend this to other file formats, so Mako and PE predominantly, but if you have any suggestions, I'm open to this as well. Other architectures, we talked mostly about the file format, but there are impacts of the architecture. So for example, the relocation entries available on x86 are a function of the x86 ISA. They're a response to the failure of the instructions to capture certain pointer semantics. All right, so I think that's about as much time as I wanted to spend, but I will show you one or two other things. Going through this project, right, because you have to generate, just a ton of different ELF files, and if you're like not the best programmer like I am, sometimes you end up with weird output, and what do you do when you have weird output, which is an ELF file? You put it into IDA, but I don't know if anyone has ever seen this error. But sometimes IDA will choke on your input. So there is a way to manipulate what are known as the segment records of an ELF file to deny IDA the ability to analyze them. So after you hit OK, IDA just closes here. And you can see in the upper left that that's IDA 7.3. So I'm one of those people that still pays for IDA despite all the free alternatives, right? The way that you achieve this is by putting the program header all the way at the end of the program in a new load record, and then tampering with the size of the load record to try to read more data from disk than there is data on disk. The Linux loader doesn't have a problem with that, but IDA does. There's also a method you can use to deny IDA information about the layout of memory. So here is the same a little bit of code I showed you earlier where you inject essentially just a call to puts. So there's the string hello world, and then the binary data after is the code that I've inserted that calls puts. So this is fine. This is the way it's notionally supposed to look. But if you tamper with the section header records, then you can convince IDA to make it look like this. And all of the code is still on disk, and it will run when you try to run something like this in IDA. So this is pretty nice, I think, because you can combine a couple of these methods to insert a bunch of code into, I don't know, something like the dynamic linker, and then tamper with some of the metadata in ELF, and then you open it up in IDA, and it looks like there's no tampering been done. Okay, so that's I think all I got. Any questions?
Did you experience the same issues with any other tools that you tried to load your Franken binaries into?
No, I didn't. When IDA failed, I don't want to talk too much. I like IDA as a tool a lot, but when IDA failed, there was another tool I used, which worked every time.
Yeah, just along the same lines. I mean, just like read elf and knobs dump, they're not affected by this. I mean, technically, with the elf spec, you can put those program headers anywhere. I mean, but you don't typically see it much.
That's right. So there. I'm sorry. Are you finished? That's right. So the techniques whereby you start moving around some of the more critical metadata, specifically the program header, that's typically not emitted by compilers. There are ways to make that look a little bit more normal. So one method that you might use is to use something like those relocation records which emit a mem copy to sort of fix those records up the way that you want them to be when they're used. I think in general, there's, I don't know, you can make it look very convincing that there's not any manipulation that's been done, but there's always going to be some delta between what a compiler would emit, especially when you may not necessarily know which compiler's code you're going to be stepping on. But you can get very close. I think you can get much closer with a solution like this than others that I've seen. You can do things like you can automatically detect and match calling conventions. You can match other kind of little compiler isms to make it look like it's plausibly emitted by that compiler. There's an issue of locality. You can do things like bridge the data sections and coalesce BSS and really these are all engineering challenges though, like it's how far you really want to take it.
Did you check? Hello. Is this good? Oh, there's my voice. Did you have a particular favorite use case, or was there a certain Franken binary that you made that was fun and entertaining?
I like that stuff use case. That's my favorite one. I guess more seriously, one of the fun ones you can do is if you're in a position where you can insert something into the system dynamic linker, that thing gets loaded everywhere. If one case where that is extraordinarily useful is if you've compromised a system that's configured to use SE Linux, and then that sort of just gives you access to every single SE Linux context. So that's good too. Yes?
You try to use version sections to do hijacking it?
One more time?
Version sections?
So I think, are you referring to like a PLT hijacking kind of technique? Is that version symbols to?
Yes, we can talk about it offline. But
For sure. I think I know what you're talking about. You sound like maybe you know the space in that particular area a little bit better. But yeah, let's talk offline. All right. Thank you very much.